In this example, we will illustrate how we can do calculus-based analysis of the properties of a function, applying it to a rational function, and then use this to sketch the graph of the said function. So again, after this discussion, you must be able to sketch the graph of a rational function. For our example, we will do a calculus-based analysis of the properties of the function y is equal to the ratio 4x to the sum 4 plus x squared, and then use the result to sketch the graph of the said function. Okay, so when you are dealing with a rational function such as this, in addition to investigating where the maximum point, the minimum point, or the point of inflection now would be positioned, we would be verifying as well on whether the graph of the function will have asymptotes. Okay, so we start with locating the critical points at which y prime, which is given by this expression, is equal to 0, or x values for which y prime would be with an undefined value. Okay, remember when we introduce the concept of critical points, okay, these are points of the curve where y prime is 0 or y prime is undefined. So on that basis, when you are dealing with a rational function, you must consider these two cases where the critical point may be possibly positioned. These are points where y prime is 0 or where y prime is with an undefined value. So working now on y prime is equal to 0, simplifying this expression here into 16 minus 4x squared divided by the square of 4 plus x squared. Now this will be 0 when the numerator is equal to 0. So working now with the product 4 times 2 plus x times 2 minus x, representing the numerator 16 minus 4x squared, setting this product to 0 would mean either 2 plus x is 0 or 2 minus x is 0, and this will give us x values of -2 or +2, where correspondingly y would be -1 or +1. Now in the case of y prime with an undefined value, this would be observed at x values where the denominator would be equal to 0. But looking at the denominator here, where we have the square of 4 plus x squared, this will be 0 when x is equal to plus or minus 2i. Now that will be an imaginary number. Now in our discussion, or in this lesson that we have for Calculus 1, we are simply dealing with real values. So when x is given by plus or minus 2i, we cannot possibly plot the point on the Cartesian plane. Okay, so the case of y prime with an undefined value now would result to x values that are imaginary and therefore cannot be plotted in the or on the Cartesian plane. So the only critical points that we have here are points where x is -2 or x is equal to +2. Okay, next is to investigate where the points of inflection would be positioned given that y prime is equal to this ratio. Working on y double prime using the quotient rule for differentiation, it will now lead us to this expression here, and if equated to 0 would give us the numerator equal to 0. Okay, so this fraction would be 0 when the numerator is equal to 0, and if we are going to simplify the form of the numerator doing proper algebraic procedure as shown here, that we just simplify 2 and -4x times 4 plus x squared times -2x squared plus 24, the product of which is 0. So the next thing to do is to determine now values of x for which this product is 0. So we can now further simplify to this form, and this product is 0 when 8x is 0, or the factor 4 plus x squared is 0, or the factor x squared minus 12 is 0, rendering these x values. So 8x is 0 when 8x is 0, x is 0, and correspondingly y is 0. So you substitute 0 in place of x in that function of y, and that will give you y equal to 0. Now, if 4 plus x squared is 0, then x would take on the positive or negative 2i value, where that will be where we have here an imaginary value, and therefore when that is substituted in that expression of y, that will also render y imaginary. Now this will simply imply that this given a point cannot be plotted on the Cartesian plane. Okay, now when x squared minus 12 is 0, that will give us x equal to plus or minus 2 the square root of 3, and correspondingly y would take on value plus or minus the square root of 3 divided by 2. Okay, so we now have located the critical points and the points of inflection. Now as we have mentioned earlier, when we are given a rational function, such as in this case of y is equal to 4x divided by 4 plus x squared, there is a need to investigate whether the graph of the function will have asymptotes, either a vertical asymptote or a horizontal asymptote. And we will be doing this using the concept of limits. So for the analysis on the existence of a horizontal asymptote, we now have to evaluate limits at infinity. If we recall, when we were discussing limits, we said if the limit of the function as x approaches either positive or negative infinity is some finite real value, then the graph of the function now we'll have a horizontal asymptote as given by y equal to whatever is the limit. Okay, so if we will do that here, evaluating the limit of 4x divided by 4 plus x squared as x approaches positive infinity, considering that initial investigation of the limit will result to an infinity over infinity, then we will be applying L'Hopital's rule here, or we can apply L'Hopital's rule to evaluate the limit in terms of the limit of the derivative of the numerator divided by the derivative of the denominator evaluated as x approaches positive infinity. And you can easily verify that the limit would be 0. Okay, so with the limit finite and real, then we conclude that the graph of the function would now be asymptotic to the line y equal to 0, which is the equation of the x-axis. Now, as to whether the graph will have a vertical asymptote, what we need to evaluate would be the limit of 4x divided by 4 plus x squared as x approaches some value a to b with an infinite limit, either approaching positive or negative infinity. It is now for us to determine what that a is. And this ratio will have a limit which is an undefined value, or this ratio here would be increasing or decreasing without bound as x approaches a if the denominator, which is 4 plus x squared, would be approaching 0 as x approaches a. And that 4 plus x squared will be approaching 0 when a is either a positive 2i or a negative 2i. Again, with this value an imaginary number, which we cannot illustrate using the Cartesian coordinate system, then we conclude that the graph of this function here, the graph of that function here will not have any vertical asymptote. The result of our analysis can be summarized in a table like this, indicating our points of inflection at x equal to negative 2 square root of 3 and positive 2 square root of 3. The critical points at x equal to negative 2 and x equal to positive 2. And again, if you work on intervals of x values representing points to the left or to the right of a critical point and a point of inflection, you will be able to come up with these intervals, and then you can easily verify f prime and f double prime values for this axis, coming up with these conclusions. Okay, so what do we do next? We consolidate everything and we sketch the curve. Okay, as a result of our analysis, we will be able to sketch this curve. Take note that we observe the minimum point at x equal to negative 2, the maximum point at x equal to positive 2, and the curve changes concavity at 3 points, at negative 2 square root of 3, at 0, and at 2 square root of 3. And the curve is observed to be asymptotic to the x-axis. Okay, so the x-axis is the horizontal asymptote, but we don't have a vertical asymptote. Okay, a recap of what we did. For rational functions, we must determine or locate the maximum, the minimum points, as well as the points of inflection. In addition to this, we have to investigate whether the graph of the function will have horizontal or vertical asymptotes by evaluating the limits as indicated.